Okay, we'll go ahead and get started. This is Organic Chemistry 1, and we are starting on Lecture 2. So you should have looked at the Module 1, Lecture 1 materials last week during the snow day. So I'll review a little bit from that today, but we're going to go ahead and jump into it. A couple announcements first. So my name is Matt Donahue. I'm the instructor for this class. I'll make some announcements and I'll give you some time for questions if there are any. So I've submitted an email about this projector, so we'll just have to deal with the one side. Hopefully they'll get it fixed by Wednesday. First thing, please read the syllabus. So it's posted as a Word document in Canvas. Click around the Canvas course shell. So the shell is outlined in 5 modules so that they're aligned according to the textbook, not necessarily in the order of the chapters that you see in the textbook, but Module 1, which we are on now, has links to the textbook readings. So when you click on those things, it'll open up another tab or window to take you to the Pearson textbook. So make sure that you can access that through Canvas. As I said, check out chapters 1 and 2. Try to do some problems. I've put in there some assignments that are in the Pearson text. They're dynamic modules, so you go through them. If you get them right, you can progress to the end. If you get them wrong, if you get a question wrong, it sort of takes you back a little bit, helps you review. Those things are not graded. They're really for your practice and understanding. Try to log into your ZipGrade account. Make sure you can do that. Your ZipGrade ID is posted in Canvas under the assignment. You use your USM ID number as the username, and then your ZipGrade ID is the second box that you put in. You will have your exams in ZipGrade. So they're open for 24 hours. The exams are 30 questions, multiple choice. So you can do them at your leisure. Just make sure that when you're done with the exam, hit the submit button. So if you don't hit submit, it's not going to put your answers forward to be graded. So you'll have exam 0 this Wednesday. So the exam will open at 12:15. You get 24 hours to do it. It closes at Thursday at 12:15. Once that deadline passes, I'll enter the key. It will auto-grade it, and then you can go back in there and see your score, and then like a screenshot of what you got right and what you got wrong. Again, read the syllabus. Please read the syllabus. I'm not going to spend a lot of time in class talking about that, but the grading schedule is in the syllabus in the front page of Canvas about when the exams are. So basically when the modules end, that's when you'll do your exams for that module. So exam 0 is basically sort of a logic exam. Everything is self-contained. You should be able to reason your way through those questions, I would hope, within 60 minutes. Again, I would recommend you, one, open ZipGrade on a laptop. If you do it on your phone or tablet, things might be a little bit too small for you to see. The laptop or web browser is better. It gives you more screen real estate. The other thing, in terms of the grading, so you're only graded on exams. So the dates for those, again, are listed in the syllabus and the Canvas homepage. So mark those in your calendars. If you don't submit the exam or you miss an exam, those 60 points are moved into the final exam. So your module exams you do online, the only exam you'll sit in this classroom for is the final exam. So if you do miss class or miss an exam, you do not have to notify me. However, that said, you are required to take the final exam. That's the one you absolutely must take. In my advice, we're going through about 12 chapters or so this semester. We have 26 lectures. One of them was online last week. So my advice is, keep up with the modules as they're listed in the syllabus, because it's pretty easy to get behind in this class, and then you'll start feeling overwhelmed. So with that, any questions before I go ahead and get started? So I'm going to teach from my iPad. I'm screen recording it, and so later today when I have time, I'll upload this onto my YouTube channel. So if you want to review it, or if you're not here, you'll be able to see it at your leisure. Again, the bonus thing about signing up for the YouTube channel, that's 6 points. So if you subscribe, you should get notifications when these things are uploaded. I'll talk more about the points and all that stuff as the semester progresses. I don't want to take up too much time about it now, but the exams are worth a certain amount of points, and basically you're accumulating points to earn your letter grade. As a question to you, what's the percent of points you need to earn to get an A in this class? Did anyone read it?
80.
Yeah. 80. What's the normal percentage to get an A? 90. So right there is a 10% curve, right? So they basically go by the 20s, 0 to 20, that's an F. In my experience, if you do nothing in this class, you'll get an F. If you put in the bare minimum, that'll get you into the D level. If you put a little effort in, you'll get a C. The B and A, you got to work for it. But it's 0 to 20, 21 to 40. That's your letter grade percentage of those points. So as you earn points, you're working your way up in the letter grades there. So again, you'll see this type of blank slide throughout the lectures, where we're specifically going to sort of pause for questions. But as I show the slides, if you do have questions, please raise your hand and ask. Again, I'm going to try to point out as much stuff as I can that will help you recall the stuff from general chemistry that you need to know to understand organic chemistry. So with that, how many people did watch the first screencast? Okay, so I think I did these couple problems, but we're going to go through them so that everyone's calibrated on what we're doing in this module. So the title of this module is Communicating and Understanding Organic Structures. So organic chemistry is really about the study of molecules. And so a molecule is just a collection of elements with bonds, and then within that molecule there are different functional groups. So we want to understand how can we take elements from the periodic table, specifically carbon, and bond them to other elements. And so when we make these molecules, one of the things you'll see in the course of this semester is, what do we use those molecules for? So your exam 0 is on a molecule called AZT. So that's an antiretroviral drug that's used to treat HIV and AIDS. So there's about 30 questions that are going to ask you things about that molecule. So sort of a review of general chemistry. So what we're going to start with today is looking at basic CH-containing molecules. So these are called hydrocarbons. And these slides are located in Canvas under the module, so you'll see them show up before the lecture. What most students do is download them onto their tablets or computers or whatever so they can follow along, but you'll see me writing up there. I know it's kind of small, but I'm going to write things down that I think are important for you to know or apply as we move forward. So these questions are written by me. They'll resemble questions that you see on your exams. It says pentane, and then it has this collection of CHs and numbers, is the first alkane that is a liquid at room temperature. What is the uniqueness set for pentane? So let me point out a couple things, and then I'll calibrate everyone on what I mean by uniqueness. So I'm going to redraw this structure, CH3, CH2, 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 CH3. So that's a molecule. Its name is pentane, so we're communicating the structure in different ways. I said it was an alkane, and this means functional group. And so a lot of what we're going to do in Module 1 is understand the different functional groups in organic chemistry. So an alkane has carbon-carbon bonds and carbon-hydrogen bonds. So with a subset of that, there are specific types of bonds. If you did watch the first screencast, how many bonds does carbon typically form? 4. And hydrogen typically forms how many? 1. So something that can be confusing about how this is written, see how it's written CH3? Those 3 H's are bonded to that first carbon. All the carbons are bonded in a chain or a backbone. And then the H3, H2, those are the hydrogens associated with that previous carbon. So this is one way of communicating it. If we were to sort of dial it back more towards the Lewis dot structures, we would draw all the carbons in a line first. And so if we know that carbon only forms 4 bonds, I put these numbers in here. Those numbers are just telling you the number where the carbon sits on the chain. So carbon number 1 shows how many bonds? Well, as it's drawn now, it's just showing 1. So if we know that carbon always has to have 4 bonds, we're showing 1. The 3 remaining things are going to be hydrogen. So that's what the CH3 means. And we're gonna learn a lot of terms this semester, and the terms really help us identify sort of where in the structure something is. A CH3 group is called a methyl group. METHYL, methyl. So carbon 2 is showing 2 bonds. So 4 minus 2, it has to have 2 hydrogens. So a CH2 group is called a methylene group. METHYLENE, methylene. So carbons 3 and 4 are also methylene. And then carbon 5 is another methyl group, CH3. So as we look at that, every bond that you see is a single bond. So that's called a sigma bond. And so how many electrons are in a single bond? So there's 2 electrons. So we know from our Lewis dot convention that each element typically supplies 1 electron of the 2 electrons needed to form that bond. And one thing I want to sort of get you accustomed to now is, so I've drawn out CH3, CH2, 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 CH3. Then we've drawn out the C's and H's. We're not really going to use that a whole lot this semester. We're going to use a very condensed version of that. It's just called line drawing. So each carbon is going to be like a point or a vertice. And then we're not really going to show any of the hydrogen atoms bonded to carbon. When we learn about other elements, such as nitrogen, oxygen, or halogens, we will show hydrogens. But for now, we're going to condense this. And we draw it in a very specific way. So let me draw it, and then I'll point out how it relates to these other 2. So that's how we would draw pentane in this course. And so this is the start of the chain right here. And then this right here, that's the line, that's the bond. And then where 2 of these lines meet, that vertex or vertice, that's another carbon atom. So we have 1, 2, 3, 4, 5. And so you see the bonds, you imply that the ends are carbons where they meet are carbons, and then again, what I'm not showing here are the hydrogens. So you assume that because this is the terminus of the chain, we're showing 1 bond. That carbon atom has 3 hydrogens. This carbon atom, we're seeing 2 bonds, so it has 2 hydrogen atoms. And then the same for 3 and 4, then we get to 5, and that has 3. Any questions so far? So again, this is an alkane, and it's called pentane. So notice the ending of pentane is ANE. And the ending of this functional group as well is called ANE. So when we learn about classes of functional groups, they're really telling you the nature of what is in the molecule. So pent means 5, that's 5 carbon atoms. ANE is an alkane, so it's a 5 carbon alkane. And then I have this question, what is the uniqueness of pentane? So if anyone watched the screencast, do you want to give a brief summary of what I mean by that? So I have this form here, carbon, hydrogen, and ratio. Anyone know what that means? Yeah.
It's each unique set of carbons to hydrogen bonds.
Yeah, so the molecular formula we're dealing with, there's 5 carbons, right? And then we have what? 5, 6, 7, 12 hydrogens. So the molecular formula is C5H12. There's 5 total carbons, but within the structure we see, every carbon atom is, they're not the same, right? So when I talk about same or uniqueness, we want to understand when we look at the backbone, are some of those carbon atoms the same? Are other ones different? And then can we reduce that down to a different number? We'll do the same for the hydrogen sets because, you know, the carbons have different number of attached hydrogens. And the reason we're doing this, as we'll see in the subsequent slides, that molecular formula C5H12, I'm showing you one way of connecting the carbons, but there's other ways you can connect those carbon atoms that are different. And so as we learn this uniqueness set, that's going to help us understand what we learn in Module 2, which is analytical techniques of how do we know we have a certain substance. And so that's going to help us understand the physical and chemical properties of molecules. So let me just give you a run through to see if you catch on to the logic here. So I said carbon atoms 1 and 5 both have 3 attached hydrogens. 2, 3, and 4 all have 2 attached hydrogens. So it's clear that 1 and 5 are different from 2, 3, and 4, just based on the attached hydrogens. So would you agree that carbon atoms 1 and 5 are identical? And a way to think about that, and I'll draw it in blue here, if we sort of draw a dotted line down carbon 3 that bisects that molecule, there's a mirror plane. So 1 and 5 are the same. So 2, 3, and 4 all have CH2 groups. To a first approximation, you could say, yeah, they're all methylene. But of those groups, are they all the same in terms of uniqueness? No, why not?
The one in the middle is bonded to different types of carbons and other ones.
Exactly. So carbon 3 is bonded to a CH2 and a CH2. Carbons 2 and 4 are bonded to CH3 and then CH2. So even though those 3 center carbon atoms have 2 attached hydrogens, 2 and 4 end up being the same, and then 3 is different. So what that reduces in terms of uniqueness, even though there's 5 total carbons, we only end up with 3 unique type of carbon. And so if we're looking at the responses here, we can rule out choice A and C because the first number we're looking at is carbon. Now the second number, we're looking at attached hydrogens, and we're considering these as sets because the carbons are going to have different hydrogen numbers attached to them. And then the sequence in the parentheses are the total numbers in those sets. So let's see if we can make some sense of that. So we originally said carbon 1 and 5 were the same. That would mean that the hydrogens attached to them are the same. So that's one set. So we have 3 plus 3, that's 6. Then we said carbons 2 and 4 were the same, so that's a different set. So we're up to 2 sets now. 2 plus 2, that's 4. And then the third set has 2 hydrogens. So we have 6, 4, and 2. So that would get us to choice B is the correct answer. To point out something that you can do to sort of self-check. So see this number here, 3. That means you have to report 3 numbers here. So if we look at choice D, see how that's 3, but there's only 2 numbers there? That has to be wrong. And then the total of this, 6 plus 4 plus 2 is 12. So that's the total number of hydrogen atoms in the molecule. Any questions before I click on to the next slide? So again, to put this in perspective of why we're doing this, as we learn, the subject is organic chemistry. It's the chemistry of carbon. The hydrocarbon functional group is the simplest functional group. You have carbon-carbon and carbon-hydrogen bonds. So if we start counting from 1 carbon in a molecule, 1 carbon will have how many hydrogens associated with it? 4. So CH4, that's called methane. So methane, ethane, propane, butane, pentane. We're starting sort of at C5 here. Well, it turns out when you get to the carbon 4 count for C4H10, you can draw more than 1 hydrocarbon for that molecular formula. We're on C5 now, and it's the same thing. And the relationship of these molecules are called constitutional isomers. That means you can arrange the elements in that molecular formula in different ways to get different structures. So the conundrum is, well, if one molecular formula gives multiple possibilities, how do you differentiate them? And this way of doing that helps us differentiate them. And as we'll see a little bit later, it ties in again to Module 2 when we're actually talking about, like, if we had a jar of a substance, how do we know it's that exact substance? So here again is our C5H12 molecular formula. And I'm going to write 5 here. We know that that's pentane. But the question says there's another molecule with C5H12, but it's not a pentane derivative. It's a derivative of butane. And butane is 4 carbon atoms long. So I'm going to draw 4 carbons. And then that's just the numbers to help us. So I have 4 carbons. I have 1 more carbon remaining. I have to stick it somewhere along that backbone to make a different compound. So where should I put it that is not going to make pentane? So carbon 2. So it's 1 carbon. So I'm going to draw a line. And I say this every time I teach Organic 1. There is a lot of information. And even though things are sort of organized according to modules, how we'll progress through, At this point, I'm teaching you stuff from different modules. So like pentane and butane, that's nomenclature. Even though we won't formally study nomenclature until later in the semester, we still have to know a little bit about it right now. So when I say pentane, you should think 5 carbon atoms. When I say butane, 4 carbon atoms. Now, that molecule is not exactly butane because it has this extra carbon at position 2. This thing is called a substituent. So it's a substituent of the longest chain. And it's 1 carbon atom long. So 1 carbon atom is called methane. But as a substituent, the name changes a little bit. It's called methyl, CH3. And that methyl group is at position 2, so we have to use a number to say where it's located. So instead of calling it butane, we call it 2-methyl butane. And that has the exact same molecular formula, C5H12, as pentane. However, if we consider the uniqueness set, they will be different. So as we're looking at 2-methyl butane, how many unique carbons do you think it has? Got some 3s, got some 4s. So it'll be 4. So let's work through sort of some tables that are going to help us understand the way that is. So one way of classifying carbons is by their attached hydrogens. Those are the 4 type of carbon atoms, CH3, CH2, CH, and then a carbon with no hydrogens. They have special names. This is called methyl, methylene. CH is methine, methine. And then C is just called quaternary. So right now, we're just going to total them. We're not going to think about uniqueness. We're just going to count the total, and then we'll apply this extra question of uniqueness. In 2-methyl butane, how many total methyl groups are there? So we have 3. So 1, 2, 3. How many CH2 groups, methylene? 1. So carbon number 3 is a CH2 group. What about methine, CH? Just 1. And there are no carbons that have no attached hydrogens. So if we total that up, we get 5. So that's the total number of carbons. Now we're going to run back through those numbers and see among those different types, are there uniqueness? So we'll say total, then we'll say unique. Anything that's 0 is going to stay 0. Anything that's 1 has to stay 1. Now we have 3 types, or 3 methyl groups. So methyl, methyl, and methyl. So should that number stay as 3? Or basically, it can't go higher. It has to either stay the same or get reduced. Should it stay at 3? No. Should it be reduced? Reduced to what? To 2. So the logic here is imagine you're hiking on a path, and the carbon backbone is the path. So you're starting here and you're hiking. And then you're walking along this path. So you start on a methyl group, you hit the methine, then you hit a methyl group. You go back around, you hit a methyl group. It's clear that carbon 1 and 4 are different as you're walking along that path. But as you hit carbon 2, you go up here, you hit a methyl group. So these two methyl groups, since they're both bonded to carbon 2, they see the same thing. No matter if you start here and walk this path or this path. If you're standing on carbon 2 and you looked up or to the left, they both look like the same CH3. So even though the count is 1, 2, 3, these get reduced. They're the same thing. So this number 3 is going to become 2. And so that's going to tell us we have 4 unique type of carbon. And so the answer is sort of canned for you. So A, B, and C are all out. So D is correct. But now let's look at the hydrogen sets. Let me first just say that these numbers here, they're not always going to be the same. It may seem that way, but they won't be. So on the correct answer, it says there's 4 sets. We said these methyl groups were the same. That's 1 set. So that number should be 6. CH, there's only one of those. That's going to be the 1. CH2, there's one of those. That's the 2. And then the CH3, that's the 3. So on the exams, I just typically list these in descending order. So they're not necessarily attached to any specific carbon numbering of the backbone. So 4, 4, 6, 3, 2, and 1. Again, since this number is 4, we need to report 4 numbers there. And these numbers must be the total number of hydrogen in the molecular formula. Any questions? So there's one remaining constitutional isomer with C5H12, and it's named as a derivative of propane. Propane is the 3 carbon atom alkane. So 1, 2, 3. So we're showing 3 carbons. We have to add 2 more. And we do not want to make a compound we already made. So where do those 2 carbon atoms have to go? So both on carbon 2. So that's A. So the logic of this, as you're figuring out these constitutional isomers, you're never going to add a carbon to the end of the chain. They always have to be internal. So we add 2 carbons. They're both on position 2. They're both 1 carbon atom long. And so a bit of the nomenclature, this is called 2,2-dimethyl propane. So C5H12 has 3 total constitutional isomers. We've now differentiated them by name, structure, and then we still have to do the uniqueness of the last one. So how many unique type of carbon does 2,2-dimethyl propane have? Heard some 3s. I heard a 2. It's going to be 2. One of the things you'll have to get used to doing in this class is, again, you're walking that carbon backbone and you're looking for basically symmetry. Do things look the same when I'm looking this way and this way? Notice carbon number 2. How many bonds are being shown? There's 4. So it has how many attached hydrogens? None. Because that has no attached hydrogens, that's a unique carbon. Every carbon bonded to it has how many attached hydrogens? 3. So all of those groups are the same. This, and this are all of the same type of carbon. So in terms of the uniqueness, there's 2 unique type of carbon. How many unique type of hydrogen? Just 1. And then the total number has to be 12. And so again, the reason for showing you this now, the structures, the name, those differentiate the constitutional isomers, but the uniqueness set is going to help you interpret spectroscopic data when we start seeing that. So what do I mean by that? So right now, that's just a structure on paper. And you can see it, you can count the carbons, you can count the hydrogens, you can generate the molecular formula. But what if I presented to you the data and then asked you to figure out what is the structure from that data? The carbon NMR of this is going to show 2 signals. The proton NMR of it is going to show 1 signal. And then if you recall back from the other 2 constitutional isomers, those numbers were different. So just by looking at the data, you'd be able to deduce which constitutional isomer is being presented. And the reason that's important is because when we do start learning about reactions, which is not until like module 3, a chemical reaction, a starting material, is going to produce maybe 1 product if we're lucky, but most of the time it's going to produce multiple products. Those products are generally constitutional isomers of one another. And part of your learning experience is figuring out from the data that's presented which product was produced in the major amount. Which product is the minor product. And then as we learn the reactions, we'll learn about mechanisms. How does the reaction actually take place? And then how does that influence the product distribution? So now we're going to start with the 6 carbon atom alkane. So this is going to be C6H14. And so that's called hexane. How many unique type of carbon does hexane have? 3? That makes sense. So let me just say 1 is equal to 6, 2 is equal to 5, 3 is equal to 4. So that's 3 type of carbon. Again, C2 to C5 they're all methylene CH2. But their unique bonding environment is going to help differentiate them. Carbons 2 and 5, the CH2 groups, on one side they're bonded to CH3, on the other side they're bonded to a CH2. Carbons 3 and 4, CH2 to the left, CH2 to the right. So that's what differentiates the CH2 groups in the internal part of the chain. Questions? So as I said, ways of classifying carbons are by their attached hydrogens. So CH3 is called methyl, CH2 is called methylene, CH is called methine, and carbon with no hydrogen is called quaternary. And this question is asking you the total number of each. So keep in mind, we're not doing the uniqueness part right now, we're just doing the total part. How many total CH3 groups are there? So there's 2, we can get rid of B and C. How many total CH2 groups? So 4, we can get rid of D. So A is going to be the correct response. We have no methine and no quaternary carbons in hexane. So what you see here, I apologize for the gray scale. I'll shut the lights off for a second, but not so long that you fall asleep. This is a simulated spectrum of the carbon atoms in hexane. On the x-axis are numbers called the chemical shift. There's not really a y-axis, but if there was, we would just call it abundance. If you're looking along this, how many lines rising above the x-axis do you see? You see 3. And in the first question for hexane, there were how many unique type of carbon? 3. So hexane has 3 unique type of carbon, and this is how they're represented with data.
So we sort of already answered this. We agreed there were 4 total CH2 groups. Are all 4 CH2 groups identical? And so again, the answer is no. If carbons 2 to 5 are all identical, then you would only see 2 signals in this spectrum. So the signals are equal to the number of unique carbon atoms. When we get into Module 2, we'll talk more about the location in which you see those signals on that x-axis. But for now, all we're doing is counting. So the uniqueness set for hexane, we already said there were 3 carbons. So we can get rid of B and D and A. So I've canned this one for you as well. There's 3 unique type of carbon. There's 3 unique sets. So that's 3 numbers of hydrogen. So we said 1 and 6 were equal. They're both CH3 groups. So the total number of hydrogen is 6. 2 and 5 were equal. So that's 2 and 2, so that's 4. 3 and 4 were equal. So that's 4, and that gets us our 14 total hydrogens. Questions on the logic? Yep. Yeah, so one thing, again, that I will capitulate about interpreting these structures, the way that you see me drawing it, that's called zigzag. And you do have to do a little bit of mental gymnastics to find the symmetry, why I'm saying 2 and 5 are the same, 3 and 4 are the same. I could draw that structure in a different way where it would look a little bit more obvious. That's the same structure. And so if I use the blue pen, now I can show the mirror plane of symmetry there, where you can see the left and right side mirroring one another. If I did that same thing up here, that would be a little bit harder to interpret just because it's zigzagging up and down. So one thing you'll want to understand about this course is sometimes students will look at those 2 structures and say they're different. They're not different because when a carbon atom and a carbon atom are bonded by a sigma bond, a single bond, those bonds will rotate. And the lower structure is just a different representation of the upper structure where you've had some bond rotations happening. We'll talk more about that in Module 3, about conformational analysis. The CC and the CH connectivity as shown is the same in both of those. We've just done some bond rotations. We call this linear. When you draw the carbon atoms in a line for the maximum number of carbons, that's linear. when you drop down from that maximum number, they're not linear anymore, they're called branched. So on this slide, it's showing you all of the constitutional isomers remaining for C6H14. So let me backtrack a bit. So all the constitutional isomers on this slide are branched. That means when you're walking along the backbone, you hit a different path, so it's branching off. And so here you can see just going to draw a line arbitrarily right here. So those longest chains are 5. These longest chains are 4. So to repeat, there's only ever one linear constitutional isomer. When you get down to the lower carbon count, the branching ones, there can be more than one. So it says, which of the following constitutional isomers has the greatest number of unique carbons? So as you think about this, again, we're going to talk a lot about symmetry. There's many elements of symmetry. So a mirror plane is one element. Like if you slice yourself in half, your right hand mirrors your left hand. There's other elements like rotations, inversions, that sort of thing. So a whole molecule can have like an internal plane. So that'll help you with 2 of these. And then the other 2, a section of that molecule can have a little plane that renders groups equivalent. Anybody got an answer? Yeah. Huh? C? No, that. There's some A's. How many unique carbons does A have? 4 is a bit shy. 5. So I'll do some coloring here. Again, I'm using an app. If you have colored pens, that tends to help students figure this stuff out. So I'll just do some coloring. So here's 1. Those are the same. That one's different. This one's different. The next one's a CH2, but it's different. And then the last one is in black there, so that's different. So the mirror plane for this one is sort of localized right here. That makes those 2 methyl groups the same. How many unique carbons does choice B have? 4. So B is one of those where it overall has like a molecular plane of symmetry. So I can draw that line right here. So that group and that group are the same. This group and this group are the same. This one's different. And then this one's different. So that gets us 4. What about C? How many unique carbons does that have? It's going to have 4. All these 3 methyl groups are the same. They're bonded to a carbon with no hydrogens. You have a CH2 group and then a CH group. Now, hopefully, if you're thinking about it, or I'll just explicitly say it, of these branched ones, now you have this issue. 2 of them have the same number of unique carbons. So ultimately, when you figure out the hydrogen sets, you'll see that that will be different, and that's how you differentiate them. And then D, how many does D have? 2. So 2, again, you got to do some mental gymnastics here. There's a plane of symmetry, and then here's a plane of symmetry. So the methyl groups are all the same, and then the methine groups are the same. So that's 2. And I will, tell you, again, the more problems you work in this class, the more you'll start developing an intuition. If you don't do a lot of problems, your mind will get stuck on looking at a molecule a certain way. And then you'll have trouble, visualizing these different planes of symmetry and that sort of thing. So 5442. Now here is those same constitutional isomers, but now you're given a piece of data. How many signals do you see in that piece of data? So you see 2, so it belongs to what structure? So D. So we figured out there were 2 unique type of carbon, so it should show 2 signals. Now this question deals with the hydrogen set ratio. So there's the unique carbons. We didn't explicitly ask about the unique H sets, but it's telling you in the question which one has 4 unique hydrogen sets in a ratio of 6 to 4 to 3 to 1. So B. So the red dots are going to get you 6. The blue dots are going to get you 4. The green dot gives you 3, and the yellow dot gives you 1. If we did the same exercise for choice C, how many unique set of hydrogen does C have? 3? Does that make sense? It can't have 4 because that carbon atom has no attached hydrogens. So it's got to be less. So it's going to have 3, and then the ratio is going to be 9 to 2, 9 to 2 to, let me write it in descending order. 9, 3, and 2. So this number, 4 and 3, and then the ratios help us differentiate those two constitutional isomers because that first number was the same for both. So what's new on this slide this is a spectrum for the hydrogen sets. What you'll notice is that these signals that come off the x-axis now look different. They don't look like a single line. I want to point out 2 things. If you just count, we would say that's one signal. This is a second signal, that's a third signal. So that's what we mean by hydrogen sets. The highlighted number in yellow underneath, that's the ratio number. So 3 sets in a ratio of 9 to 3 to 2. And so as we just saw, that belongs to structure C. So let me use some alternate nomenclature here. If I said this is A prime, B prime, C prime, and we're still talking about structure C. What do you think the signal at B prime belongs to?
That group on the top.
Say it again.
That group on the top.
So see these groups here, 3, 6, 9. What that piece of data is telling you, the signal belongs to the hydrogens in that set. And that's what the number underneath is telling you. So C prime would belong to what? See, that's 3. And then A prime would belong to that because it's 2. So when we learn about actually interpreting this data a little bit more, this number is called integration. And for now, we're just calling it a ratio. Any questions? There's our question slide. So we have 5 minutes left. I'm a stickler for using the maximum amount of time. You're paying for it, so I'm going to give it to you. So we'll end at 12:15. Sometimes we might go a little bit over, but not much, because I got to hoof it over and teach my other class after. So what you just saw now, in the first 70 minutes of this lecture, that's what you should expect on exam 0, those type of questions. They're self-contained for the most part, that you should be able to deduce the correct answer. So I want to get into this next part before we wrap up today. As I said, hydrocarbons are C and H only. As we learn more functional groups, I'm going to use this term heteroatom. And that's anything that's not C or H. So nitrogen, phosphorus, oxygen, sulfur, halogens. So we're only talking about CH compounds. And as we saw today, the functional group is called alkanes. So every bond in there is a single bond. Another way of saying that is those are fully saturated. And this will become a little bit more apparent or clear as we introduce this stuff. Then we're going to dial it back down to atomic orbitals, how those things can do some stuff to form hybrid orbitals. But when we say saturated, we mean sigma bonds. We can also have unsaturated hydrocarbons. And those have carbon-carbon pi bonds. So it's a sigma bond plus a pi bond that gives you a double bond. When there's a double bond, that's called an alkene. So notice the name change is subtle. It ends in ENE. When there's a triple bond, those are called alkynes, and that ends in YNE. And the point I want to make clear to you now is when you're given a functional group name like alkyne, somewhere in there is a carbon-carbon triple bond. So if you're scanning the answers on an exam and the choice does not have that, it's got to be wrong. And we'll talk a little bit this semester about aromatic compounds, but that's really 256. And an aromatic compound is a ring that has double bonds in it. So hydrocarbons really are isolated from fossil fuels. And those fossil fuels really are the starting point for pretty much everything we use in human civilization. And the big picture of this, what is the relevance to you in your degree major? Why are you taking this? It's important for you to understand not only structure, but chemical reactions that make things. And on your exam 0, you'll see a little bit of an introduction about that molecule AZT. It's not found in nature, it's made in a lab, and it has a very specific purpose of treating HIV and AIDS. And so one of the first reactions that you will learn is taking an alkane such as methane that's nonpolar. It has these physical properties. Treating it with chlorine gas to do a substitution. See this hydrogen? That gets substituted for chlorine, and that makes a new functional group called an alkyl halide. So chloromethane is now a polar molecule, and its physical properties change drastically. So we're going to end here for today. We'll pick up on alkanes, alkenes, alkynes. We'll draw more constitutional isomers. And then we're going to play a game or see how many we can figure out per molecular formula. The screencast will be posted in YouTube later today.